All right, good morning or afternoon, depending on where you are. Welcome, everyone. Thank you so much for joining us today. My name is Alyssa Sleeva. I'm the head of marketing for Prescient Transmission Systems. Prescient is an electrical engineering consulting firm specializing in risk assessments and next generation concepts for the electric power grid. This is the first in a series of webinars that Prescient is presenting on electric power industry topics. So now I will turn it over to our keynote speaker, Tony Sleeva, President of Prescient Transmission Systems.
Hello, I'm Tony Sleeva. I'm a life senior member of IEEE. I'm a registered professional engineer. I've worked for many electric utilities throughout the United States. I worked for one utility for 30 years and then joined the architect engineering firm and became a contractor for 20 years. And for the last few years, I've been working at Prescient Transmission Systems. Today, we're going to be considering wildfire risk and wildfire risk considerations, the factors that are important for wildfire ignition, how you determine the risk, and enhancements we can do to prevent wildfires. Wildfires cause catastrophic losses, loss of life, loss of property, natural area, forests, and power companies can be held responsible for everything. The wildfire season is lengthening, and that's due to climate change. And everyone is aware that power lines ignite fires. So one of the first questions that come up after a forest fire is, was there a power line that ignited the fire? We can decrease the risk of power line fires. Our goal is to decrease the risk 25% per year so that by the year 2024, this isn't an issue anymore. What we want to do is we want to reduce the fault durations. We want to reduce the amount of energy released at fault locations. This means we have to understand moisture, we have to understand the vegetation that's nearby and the moisture content of the vegetation. We'd like to understand the distance between an arcing fault and nearby vegetation. And we're trying to eliminate preemptive blackouts. Preemptive blackouts are a last resort that right now we're using them more often than we'd like to, but we should be able to eliminate preemptive blackouts. When you think about wildfire ignition, heat is coming off sparking power lines. With hot summer temperatures, what you do is you increase the temperature of the dry vegetation, you reduce the moisture of the dry vegetation, and you increase the likelihood of the uncleared tree growth and uncleared brush piles igniting. If you have high winds, replenish the oxygen quickly. And one of the keys is understanding how far it is from a sparking power line to dry vegetation. When I'm looking at calculating wildfires, there's a whole bunch of items I have to consider. First is the material ignition time. And if I can clear faults before materials ignite, then I won't start wildfires. I want to know the material ignition temperature. Typically, the material ignition temperature is around 450 degrees Fahrenheit. The material temperature is going to start out at ambient temperature plus solar radiation. So the material may start out at 120 degrees Fahrenheit. I want to know how much energy is released at the fault location, and I want to know how much energy is deposited on dry vegetation. Once the energy is deposited on dry vegetation, I want to find out what the density of the material is, and I want to know how thick the material is. A thin material is going to ignite much quicker than a very thick material. So the key concepts we're worried about are time and distance. If I clear faults quickly and I keep dry vegetation far away, I'm not going to ignite fires. The amount of energy I deposit on dry vegetation is a function of distance, and the energy I release is a function of line voltage, fault time, and fault current. Line voltage is important because As line voltage increases, the length of an arc is going to increase because the size of insulators are greater. Then I also want to consider what type of fault do I have? Do I have a single phase fault, a phase-to-phase fault, or a three-phase fault? I like to think of wildfires and compare it to toasters. If I have a toaster, I get put bread in a toaster for 3 minutes and I get breakfast toast. 6 minutes, I get burnt bread. 10 minutes, the smoke alarms are going off. You got to remember that when I'm toasting bread, I'm only putting 10 watts per square inch on the bread. This analogy isn't the perfect analogy because there's a good deal of residual moisture in bread. If I take my bread and put it in a microwave oven and let it in the microwave oven for 30 seconds, it becomes soft and squishy. And you'll actually see that some of the moisture came out of the bread and deposited on the plate that you put in the microwave. So 3 minutes is breakfast toast. If you put absolutely dry vegetation in a toaster for 3 seconds, it would be smoking. So what needs to be done? Well, you have to calculate the risk. You have to classify the risk. You have to enhance fault detection. You have to manage combustible materials, and you have to update your power line designs. When we're looking at a wildfire risk assessment, we look at your protective relaying schemes. We look at the distance from a substation, and we look at right-of-way conditions. We've developed algorithms that give me combustible material ignition time, and that combustible material ignition time is a function of fault clearing time and energy deposition. So if you look, I've got a typical overhead radial distribution line here. This is a 7-mile line that's routed through forested areas, and there are reclosers along the line. So at the substation, I've got an 800 amp circuit breaker. Between miles 1 and 2, I've got a 100 amp recloser on a tap. Between miles 3 and 4, I have a 400 amp recloser in the main line. And between miles 6 and 7, I have a 200 amp recloser in the main line. So this is the basic line for a distribution line overhead that I've got today. And the way we analyze this is we plot ignition time versus distribution line miles. Normally, when you're looking at things like this, our traditional thing is we use time current curves. And time current curves have time on the vertical axis and amperes on the horizontal axis. For wildfire ignition, it's better to use distribution line miles on the horizontal axis and to change the axis from a logarithmic axis to a numerical axis. So on the time, we're still using logarithms. The plot is from 10 milliseconds to 100 seconds, and the distance starts at the substation and goes out to 7.5 miles. On the first mile of the line, I can clear faults using instantaneous relays at the substation. Between mile 1 and mile 1.5, this is where time overcurrent relays are going to operate. At mile 3, this is where a recloser starts operating. And at mile 6.5, that's another recloser. So the clearing time that I'm showing here for faults on the black line, this is assuming that I have the standard protection schemes today, where I have a fault, I trip, I reclose. If the fault is still there, I trip again. I reclose, I trip again. If the fault is still there, so I have 4 trips and 3 closes is the standard trip close cycle on an overhead distribution line. And the red line here, this is the ignition time of dry vegetation. And you can see that between mile 1.5 and mile 6.5, dry vegetation is likely to ignite before the fault is cleared. So what I want to do is I want to come up with a clearing, wildfire reduction clearing time, the green line down here. The green line shows faults cleared in 100 milliseconds. And the way I get faults cleared in 100 milliseconds is the first thing I do is I disable reclosing. So if I disable reclosing, I'm only going to get one trip. In addition to disabling reclosing, I'm going to use more sensitive settings. The more sensitive settings I use should be a function of the ambient conditions where I am. In the rainy season, it's okay to use the black clearing line because the vegetation ignition line during the rainy season wouldn't be this red line here, but it will be moved up because there's a lot of moisture. You have to get the moisture out of the combustible material before it catches on fire. So what we're looking at is dynamic settings, and the dynamic settings will be a function of the ambient conditions where we are. So we want to calculate the energy released with fault condition. We do a calculation for three-phase faults, phase-to-phase, single phase. We include arc resistance, and the amount of energy that you release varies with clearing time. But varying with clearing time doesn't really demonstrate how well you're doing. A much better example is right here where I'm putting, instead of time, I'm putting distribution line miles, and I'm comparing the ignition time as a function of mileage. The values that we're calculating are watt seconds per square inch. The risk matrix we use, it looks at power line location and voltage, combustible materials, protective relay applications, and firefighter response time. If I look at the graph here, table 6.3, the concentration is when I have a large concentration of combustible materials. If it's an urban area, firefighters and nearby equipment can get to the fire. It's not a big deal. Where we're concerned mostly is remote areas. If I have a remote area with a high concentration of combustible materials and firefighters are going to take a time to get there, that's the highest risk, risk level 4. Risk level 3 would be a high concentration of fire with equipment firefighters can get there relatively quickly, or it would be a moderate concentration of combustible materials that firefighters have trouble getting to. So you have to look at all these things and evaluate. We're not proposing a one-size-fits-all. What we're proposing is that you actually classify the risks that you've got, and once you classify the risks that you've got, then you modify your system so that everything works out well. Strategic enhancements that you can do to reduce wildfire risk. You have to update your protective relaying design practices for rapid fault detection and isolation. Right now, I'm setting my protective relaying up so that everything coordinates. If I go back a couple of slides, the way I set this up is if I have a fault at mile 5, the 400 amp recloser is supposed to actuate, and the 800 amp circuit breaker to substation doesn't actuate to isolate a fault at mile 5. If I have a fault on this tap, I'm going to trip the 100 amp recloser, and I'm not going to trip the circuit breaker back at the substation. When I'm in an extreme wildfire risk, I have to discard coordination as my main criteria. My main criteria is isolating faults before I ignite vegetation. So I'm going to update my protective relaying practices so that during the dry season, when temperatures are high and residual moisture is low, I'm going to clear faults as quickly as I can. This will minimize energy deposition from arcing faults. The energy deposition is a function of distance and time. If I can get the time down to 100 milliseconds, then I'm going to really minimize the probability of a fault igniting a wildfire. Now, the 100 milliseconds is based on typically circuit breakers are 3-cycle circuit breakers, which mean they operate in 50 milliseconds. And the relay time is about 20 milliseconds. So I'm thinking I should be able to clear faults in 70 milliseconds, but I'm plotting it at 100 milliseconds. And I want to designate combustible material free zones, and I want to improve power line construction. So if you're looking, how do I get combustible material free zones? Best management practices today are not good enough. Today we're looking at clearing hazard and danger trees, but dry vegetation near a power line can ignite. And I don't want that to happen. So what I have to do is understand the ignition time of dry vegetation, and I have to understand how far away things are from power lines. I have to look at horizontal clearance, vertical clearance, and then I have to look at the different fault types I can get there. I can get a broken cross arm, I can get a down pole, I can get a tree across the conductor. So you should look at all these conditions and make sure that you've evaluated the dry vegetation, the amount of energy you're releasing, and the ignition time of the dry vegetation you have. When I talk about improved power line construction, I see a lot of things we could do to improve power line construction. For example, I see people putting hot line clamps directly on a power line. If the hot line clamp works free and causes a hot spot and damages the conductor can fall down and go on the ground. There's a high probability that would ignite a wildfire. So a thing we can do is to put stirrups on, so that what you do is you actually swage a stirrup on the power line and then put the hot line clamp on the stirrup. If the connection becomes loose and the hot line clamp falls to the ground, it's not a power source anymore, and you're not going to ignite dry vegetation. And when I get to areas where wildfires are risk, I should be using robust falling conductor prevention, which basically means what I want to do is harden all my connections so that I don't get a falling conductor. A conductor doesn't fall off in the wind and doesn't ignite a wildfire. So I'm looking at enhanced protection, enhanced power line construction. There's a lot of things we can do to make the system more resistant to wildfires. So one of the things that Prescient does is we develop risk assessments. And the risk assessments, it's basically a report. We look at one of your power lines and we present a report which has an executive summary. It provides the technical details and the explanation of everything we've looked at. It provides simplified maps of the power lines and then wildfire ignition mileage charts. So what we prefer to do is to actually walk down a power line, point out where the protection is on the line, point out where protection can be improved, point out things we've seen that could improve the construction of the line. And we use a risk matrix to determine a specific score. And then what we do is we can look at the risk score and look at the improvements we recommend, like protective relaying changes, and tell you if you change your relays from electromechanical to microprocessor, and if you use your microprocessor-based relays with setting groups that vary with ambient temperature or wind speed or a weather history, that would change this risk score. So these are things we can do, and they're things we should be doing. Electric power companies need to know the risks they face, and they need to know the potential consequences. We're here to identify changes they can implement and to show power companies things they could do to become industry best.
Your risk assessment in that, how long does it take to do that kind of work, physical work?
Typically, if we're looking at a substation, we would look at a distribution substation. And if I have a distribution substation with 4 overhead power lines leaving it, we can perform a risk assessment in 30 days. So within 30 days, we would look at the protective relaying on the line, look at how the lines are laid out in the area adjacent to the substation, and provide a report that outlines our findings. And we're thinking it would take us 21 or 3 weeks to do that. And then after 3 weeks, we would give it to the host utility to review for 1 week. so that in 30 days we would have an example of what we can do for them.
The other, well, following along the same line here, then, so what does this cost for your example you gave?
Yeah, for a substation with 4 overhead distribution power lines leaving it, we're thinking that the cost on that will be somewhere less than $10,000. So thank everyone for attending. If you have any comments or any future questions, reach out to Alyssa and she will get them for you.